Today I'm going to be talking about sound. I'm going to talk about how sound is created, what creates sound. And as you probably have an idea of, is that sound is a wave, right? Usually in in books or movies or whatever, you see sound like if this is if this is me and I'm speaking, you will see sound kind of being portrayed like this potentially. I don't know. Like when I was a kid, this is literally what I thought sound was. And another way sound is often represented is if you have let's say we have a speaker, one of those 360 speakers that just emit sound in all directions, and these and if this is our speaker, right? Sometimes you'll see sound kind of like a ripple, and the sound waves are kind of expanding out a speaker, and they aren't really. This one I'd say is more accurate. This is not really accurate to what sound really is. Here's the deal with sound. Sound is it's a wave. It's for sure a wave. What do waves consist of? They consist of oscillation, right? If I have, let's say this is a string, right? If this is like a string, then what's going on with this wave is these particles are moving up and down, right? It's a transverse wave. Yeah, transverse wave, right? The particles are moving up and down, and that the up and down movement, right? This movement moving up causes the piece of the rope next to it to move up, which causes the piece next to it to move up, and then this piece will eventually start to fall down, causing the other piece to fall down. Boom, you get a wave, right? Like it's a chain reaction of up and down movement that is carrying energy through that wave. Sound is no different than that, except instead of the air. So here's what's going on, right? When I speak, my vocal cords. Actually, yeah, let's go down to the vocal cords. I guess that will kind of make the most sense. So what my vocal cords are doing is they're oscillating at a certain frequency, right? And that frequency is causing the air around it to oscillate. But instead of the air oscillating like perpendicular to the direction of the wave, right? It is moving with the direction of the wave. So let's say my wave, so if I don't know what vocal cords look like, so maybe I'll draw like a harp. Maybe those are my vocal cords. It's just a harp. So if these are my vocal cords, right? What's happening is the vibration of the vocal cords. I'm not a biologist, so that's probably simplification. But those vibrations are causing the air molecules here to jolt forward, right? They jolt forward. And as they jolt forward, these air particles, which were initially like still, it's gonna get compressed. They're gonna get compressed like so. And now so let's say this is like T at 1 second. I don't know. And then we have some air molecules like so that are normally just spaced out. But we have this compression right here. And what happens after a certain amount of time, T2, is then the second layer of molecules moves forward. And then these molecules right here get pushed back, right? The original molecules are going to collide with ones in front, causing the front ones to move, and then the original to kind of move back. And then you will get something that looks a little more like this. And then eventually what might happen is then, the air molecules behind it push it back forward. And the whole idea is you get like a series of compression and then no compression. No compression and then compression. And you can see, and like a point right here, right? There's a lot of compression. There's a lot of pressure. Here, there's very little compression, right? Very little pressure, I guess. I'll get more into that in a second. But pressure, no pressure, no compression. I'm saying pressure because when you bunch up a bunch of air molecules together, they're exerting forces on one another, and by the time this sound wave, right, with these molecules, right, they're moving back and forth. This molecule, right, if this is my ear, I don't know what an ear looks like. If this is my ear, these molecules are never going to meet my ear. Unfortunately, as amazing as my ear is, these molecules never going to reach it. They're just oscillating back and forth, creating that pulse, that wave that my brain will eventually hear as a sound wave, because eventually the air right by my ear will start vibrating. That I perceive as sound. So that's kind of like an intro to sound waves. Hopefully that makes sense. Why do sound waves get associated with this shape? Well, if I draw like a pressure versus distance graph, you can see, if this is where I'm saying x is 0, right? If this is where I'm measuring the anatomy of a wave, at that initial distance 0, the pressure is really high. And then there's going to be a point where I say pressure is kind of like pressure is 0, or maybe like because I believe, I mean, there's still got to be pressure at the equilibrium spot, right? And equilibrium in this case is just when the particle is at its original position before it started moving. So, you know, you can, and then maybe when there's a rarefaction, which is when there's no like very little compression, it's like the trough of the wave. You can see, it makes like a wave that you would normally associate with like waves in general, right? You don't see this and think of a wave, you see this and think of a wave. So that's kind of an intro to sound waves. Thank you for watching. Hopefully, oh my god, my hair was parting. That sucks, but hopefully that kind of made sense.